Hi, everyone, and welcome to our monthly virtual lecture. Just a reminder that the lecture is being recorded and it's going to be available on our YouTube channel in the coming days. I'm Carla Gonzalez, and I'd like to introduce you to our speaker today, Dominique Fournier. Today, he's going to show you how to use the Peak Finder Geo app for the detection and grouping of time domain electromagnetic anomalies measured along flight lines. If you have any questions during the presentation, feel free to type them into the Q&A or raise your hand. Though please be aware that Dom may wait till the end to answer the questions. And whenever you're ready, Dom.
Thank you, Carla. Back to be back on your show, the Carla show that we call it at Mira. It's been a while. Okay, so yeah, I'm Dom. I'm a scientific programmer at Mira Geoscience. And yeah, it's my pleasure to demo today the Peak Finder application that we've released about 2 months ago on the GeoApps version 0.3. Maybe just a 2-minute reminder what the GeoApps are. So hopefully you see on my screen right now the landing page. So if you just Google GeoApps from Mira Geoscience, you should be able to find it. And then basically the brief explanation of what the GeoApps are is our sandbox to be able to prototype ideas to solve any type of geoscientific problems, mostly right now targeting, of course, mineral exploration. And then there are 2 goals to this. One of them is that we obviously want to increase the attraction, or like bring more people to start using Geoscience Analyst. And then the second part is that that gives us basically an easy way for us to prototype ideas at low cost before we bring them on to a Geoscience Analyst, the main software development team. Okay, so basically, as I said, this is a fairly new application, the Peak Finder that I'm going to show you now. So if you have comments, good or bad, send us our way. It's much appreciated. So this way we can make things better, and then see if there's interest in it. Okay, so yeah, without further ado, so here's the Peak Finder, the documentation for the Peak Finder. I'm going to go down the details in a short moment. But basically the idea is that, let me just find I have a cartoon here. Basically, the idea is that if you're measuring data along line, let's say an airborne EM survey, this was specifically designed for time domain EM, but could be used for other type of data. But if you're an EM system, you might see bumps like this in your data, right? So those are like basically time channels measured at various times. So it's a decay data, right? And then the distance along line. So we had a user, a client, who asked, "It would be great if we could automate the picking of those anomalies and the grouping of them, right? So if you see a bump like this on a time channel, can you find the same bump on like subsequent time channels? And if yes, can you group them in some way, right? Compute tau and all those extra parameters or extra derived data, I guess. And so this is what this application is doing. So it's nothing fancy. You know, there's other groups that work on machine learning algorithms to do the same thing. Here we went for call it the KISS approach, keep it stupid simple. We're just going to do a long line, find all the maximums and the minimums, and then that defines a bump. Okay, so that's what I will demo today, how to tweak the parameters for the automation of the selection of those peaks, and how does it look in Analyst when we export it back. All right, so this is it, and I thought for this demo, I could have used a synthetic data set, but I thought it would be do something a little bit more interesting. I was involved on a project not so long ago, sponsored by Geoscience BC. So I'm in Vancouver, right? I sit somewhere here on the coast. And then we have this really interesting problem in BC that we have this, this large area, and here I'm just going to show you in Google Earth quickly all the mineral occurrences and previous deposits in BC. And then there's this interesting area here where, you know, there are known mines on either side. And then there's this big gap, right, where there's nothing in the, no major discoveries found in between. And that's because there is about like 100 meters of sediments that covers it. So it's really, it's risky for mineral exploration. So there's not much has been done there. And then to be able to help this and then, you know, promote exploration in BC, Geoscience BC sponsored a large VTEM survey over the area. In 2007, this project was basically released. And then today I'm going to look at this VTEM data set. And we'll try to maybe tease out some extra information if we can with the peak finder. Okay. So I did the same thing here. This is now Geoscience ANALYST that you're seeing. What I did is basically simply downloaded the data from the Quest site. They were in a GDB format, and then I just merged them all into one large survey. So those are the lines. And then the points that you're seeing behind here are the mineral occurrences that I've shown you before, right? And I flagged a few important ones like Mount Milligan sits here, right? So it's covered over the survey. And then on the other side of the gap that is here, we have a few other mines like Mount Poly and so forth. All right, so we'll be focusing on this area here. What's quite interesting about this data set, and that's why I'm going to be using it today, is that here I'm using the 2D profile viewer to show you basically one section of line near Mount Milligan, right? So here I'm showing you basically the VTEM data right near the Mount Milligan, right? So early time, and then we can cycle all the way to late time. And then what you'll notice, and which is quite interesting, are those large negative EM signal. And this is, you know, pretty hot topic in EM world right now. Negative time decays like this for a coincident loop are thought now, and, you know, pretty strongly advocated to be a signal for IP. Right, to be indicative of an IP response. And you can see this, right? It starts positive and it goes negative for a while. So I thought for this demo, instead of focusing on the positive bumps, I would try to use a peak finder to highlight all those areas where actually data is going negative, and maybe not going negative, but even just, you know, decaying very fast. So we're basically seeing a bump in the negative sense, negative sense of it. So that's what I will do now. Let me start the application. So I'm just going to minimize this for a second. If you download and install the geoapps, you have a folder that looks similar to this. And then after running the installation, you can just start the application. So we'll do this now. It will come up in a browser. So those are all the applications that are available currently. And I'm going to select the peak finder. Minimize the stuff. Okay, and then I can just run the application now. So what basically what you're looking at here is a Jupyter notebook. So we're using, again, open source code to be able to develop UIs, right? Simple user interface. So currently this is a Jupyter notebook, and as soon as I run the application, by default, it's going to log to a demo data set. But I'm not going to look at this now. I want to actually connect to my project that I have on my desktop here. So I will change, and I will go to my desktop and just select my project. And then inside my project, I have two curves. I have one for the faults. I'll show you later, but I'm interested in the compilation data set. And then I'll select the DBDT. It's SF. It's called SF for VTEM. All right, and I'll select the line. So let me select the same line as I was looking at here. Whoops, I don't want to quit. All right, so Mount Milligan, this is going to be line 126. Okay, so I'm going to be selecting line 126 in my application. 126. So basically what you're seeing here is the list of all the, there's about 100 lines, right? So I'm selecting one of them. And the way the application works is that we're first going to be tweaking our parameters for just one section, you know, on one line. And once our parameters we're happy with them, then we'll just apply the same process on all the lines, and we'll just batch the picking basically on all lines at once. All right, so I'm just going to set some parameters here so that we see where we are. You'll notice that the plotting function is quite slow. It's quite slow in the application because we're using matplotlib, which is not really optimized. So please be patient. Ideally, this would be ported inside Analyst down the road once we're pretty happy with the application. Okay, so you'd notice here that I'm basically seeing the same data as this one here. We're flipped, but it's basically this anomaly here. So I would like to be able to customize my parameters, so I picked this one up. Okay. So right now we're looking at the data positive. So I'll do one simple operation. I'll just flip my data on its head so that the negatives becomes maximums. Okay, so I'll flip the data. All right, a second. Right, so now you can see that actually the application managed to pick it. You see when it's colored, it's basically trying to group the bumps into time channel groups, and it's going to color code it accordingly. So early times are blue, mid early are kind of cyan, and then so forth all the way to late time red. You can always define those groups here, and then setting the colors. So let's maximize this. There's also you can also compute tau and look at the decay curve for sort of specific anomalies if you'd like. In this case, it's IP, so it probably doesn't make too much sense. It's just an option. And then you can also select the type of EM systems. In this case, I already detected it was a VTEM. Okay. So now my task is that I would like to be able to really just highlight this bump here. I'm not really interested in all that jitter, the near noise level here. So I'm going to explain quickly what those parameters are doing. All right, so the first one is smoothing. And I mean, this is quite self-explanatory. What it's doing here is that I'm basically doing a running mean along each time channel to be able to just kill some of that high frequency content. All right, and by just doing this, I basically smoothed out all the near zero here, just to really focus on the big bumps. All right. The second parameter is the minimum amplitude, and that basically to discriminate bumps that are judged to be too small, right? So it's going to be a % based on the relief, basically from the minimum to the max. All right, and I'm just going to increase this a little bit. Okay, let's say just 5%, and this should clean up close to these guys around here. Then the next one will be the minimum. So minimum value. So for instance, in this case, I'm only interested in what's above or near the crossover. So I'm just going to threshold my data. I'm going to put a hard cutoff on the data, so I can just put a minimum floor, right? So I'm going to do a -1 like this. So it will be basically cutting all the data down here, ignoring all the early times. The next parameter is the minimum width, and here it's basically measuring from a low to a minimum. And if the anomaly is too small, is too narrow, the algorithm will just ignore that bump. Okay, so basically this is experimentation, right? Trial and error. So last night I was trying to do it, and then you know, after tweaking, okay, this parameter, I get exactly what I want. And then once I'm happy, then I could just carry on. And the last, the second to last is the maximum peak migration. And here is that you see those peaks are pretty much lined up here. So that's great. That means that they're probably belonging to the same group. But it can happen that your peaks are migrating quite far from each other from one time to the other. So then you basically put a threshold and say, if you're migrating too far, then you're a different anomaly than this one. Okay, so I'm just going to put it again here. That's pure experimentation. So 300 meters, if you're above 300 meters separation, just consider it as a different anomaly. So you still that going from 100 to 300. Now this one is considered as one single anomaly. Okay, and then the last one, this is a discriminator on how many time channels should be in a group. If you have less than this number, it will consider that it's not an anomaly, it's not interesting, and it will discard it. And I think here at least four time channels to define a bump is sufficient. Obviously, it's not going to affect this guy here because we have 1, 2, 3, 4, 5, 6, 7, right? So this one's not affected, but it's for other places in the data set. Okay. Hopefully this all makes sense. If it doesn't, the documentation is online. You can just read about each of those parameters in greater details. Once you're happy, you just click on process all lines. And what this will do now is that apply the same process on all 100 and something lines that we have in our analyst project and on that object. Okay, so it's going to do the same process or apply the same parameters everywhere, so that we can look at it. It takes about a minute and a half to run the whole thing here. It is parallelized, but there's still a lot of calculations. So while this is happening, maybe let's just, I'll just take you quickly, just a quick reminder on how to get set up with the GeoApps. We have a minute to do this. So if you Google GeoApps again, you can go to the Getting Started, and the Getting Started will tell you how to download and install the GeoApps. And then obviously you will need Geoscience ANALYST. The free viewer is sufficient to be able to run it. So basically you can be up and running at no cost, at zero cost, and try it out at home. Okay, it's still going. Okay, so it's just done now. For those of you who are not familiar with Jupyter notebooks, when it's busy, this circle is black, and then when it's done, it turns back white. Again, when you're done, you can just click on Export All Peaks, or you can give it a name, Export All Peaks. Okay. So I already done it, so I'm not gonna reopen the project. It's kind of like a cooking show. Here's a turkey when it comes out of the oven. So when the turkey comes out of the oven, you basically have points, and each of these points mark one group, right? And then you can turn on and off what group these belong to. And in this case, I'm only going to look at the middle and late. And then let's look at how it compares to what we know about the area. And just for the sake of it, I also gridded those time channels. I forgot to show you earlier, but basically what you're looking at here are the gridded DBDT channels on the VTEM. And you can see that from early time, we already started seeing some strong negatives in certain areas. As I go later and later and later, these negatives are really pretty consistent, pretty persistent. And I notice that a lot of mineralization occurs like right next to those negatives. So I'm not saying that this is the silver bullet to find minerals in the area, but I think it's interesting. It is worth exploring further for someone who actually knows what they're doing. But I think it's quite interesting that you see those fast decays real next to the already mineral occurrences or even mines like Mount Milligan. So basically what I did here is try to pick out all those fast decays as you know, in an automated fashion, so that you could always go back and look at them. And then I can show you the identified structures in the area. Again, this is the gap, right? The area where no mineral occurrences were found. And it's interesting that the algorithm picked out, there's quite an interesting correlation with the structure. So all the yellow dots, the orange and yellow dots, right? They're kind of showing all at the same place. Areas where possibly dilation could have happened. So yeah, this is just a tool, another tool in your toolkit. Ideally, after this, you would be basically looking back at your data, maybe identifying zones of interest, using Maxwell type modeling to investigate, or straight up inversion if needs be. And that's it. That was pretty much the end of my talk. So you can switch to questions. Yeah.
Yeah, thanks, Dom. And thank you everyone who joined today. For any of you who are in the lecture, do you have any questions? You can type them in the Q&A, or you can raise your hand, whichever way. You have any questions, go ahead. If you have any questions in the future, please don't hesitate to email us at support@mirageoscience.com. Those of you who do not yet have a license for the free viewer will be receiving one shortly after this lecture. And we also look forward to seeing you next month, when I will be showing what's new in our next release, Geoscience Analyst version 3.3. So just checking again, does anyone have any questions? Questions?
All crystal clear.
Yeah, perfect. Okay, so then that's it. Thank you everyone for coming.